I'm Yu from Huaiqian University. So today I'm going to introduce our paper on developing invariant neural operator for learning complex physical systems with momentum conservation. The purpose of this work is trying to provide prediction and monitoring of physical system responses directly from data, say from experimental measurement. So traditionally, this type of the task was done by developing PDE-based models. So here is one example coming from the mechanical testing of heart valve leaflet tissue. So basically, we collect data from different loading scenarios and the corresponding material response. So that is the deformation of the material at different, corresponding to different loading. And then for the second step, we are going to choose a model. So for example, like here, we are showing the phone type model and trying to fit the curve, trying to find the corresponding, trying to fit the corresponding stress curve to find the optimal parameters. And then as the third step, then based on the learned model, we are going to use that in the downstream task, for example, to solve the nonlinear PDE and trying to provide like the further prediction of the material under different loading scenarios. So, but however, this type of the procedure hides at least two possible pitfalls. So the first pitfall comes from the model selection. So basically, when we are not selecting a good model, then it might create the modeling error. So for example, when the material and all the physical response system is actually heterogeneous, but we choose a homogeneous model, and then it's going to create the modeling error in the downstream task. And the second challenge comes from solving nonlinear PDE for the downstream task. So when the PDE is complex, then the solution procedure could be very time consuming. So that creates difficulty in the computational scalability. So then in the recent years, in the scientific machine learning community, people start to propose to use neural network as an alternative for the step 2 and the step 3. So basically, what we can do is trying to model the physical system response directly from data by building a neural network from the input function. So basically, it can be seen as the boundary condition here, which is represented as the vector G, and then to the output function. So that can be seen as the material response, that is the displacement field represented by the U at different locations here. So this type of the architecture, basically, it learns the model directly from the data. And also, once it's fully trained, then the further prediction only requires a forward pass. But however, it also presents a special challenge. So firstly, it requires the data. So in the very small data region, it could, basically the modeling error could be huge. And moreover, the traditional PDE model guarantees the basic physics laws, so such as the conservation of the linear and angular momentum. But on the other hand, if we learn that from the neural network, we might lose these physics laws. Okay, so in this talk, we are trying to resolve this. We are developing a neural network architecture to predict the complex physical response, but hoping to resolve these two challenges. So our development are based on 3 working assumptions. So the first working assumption is we assume that we have the collection of data. So basically, we assume that we have the measurements can be seen as many pairs of the input function, which can be seen as the loading function, and the output function. So that can be seen as the corresponding material response, that is the displacement field in our example. And the second working assumption is, although to avoid the possible misspecification of the model, we assume that we don't know the governing PDE. But however, we still assume that there is some hidden governing PDE, although we don't know that, that governs all these complex physical responses. So that means basically we have an unknown and possibly nonlinear differential operator. So that's the L here, which might be dependent on the complex physical basically the physical parameter field can be seen as the microstructure of the material. So that is the B here. So then with different loading scenarios, so that can be different F and different UBC, we have a different, like the physical response. So that is the solution U here. So as such, modeling the physical system can be seen as finding the solution operator of this hidden governing equation. And then the third working assumption is, although we don't know what is the governing equation, but we still assume that the physical system should satisfy the basic physics laws, such as the linear and angular momentum conservation laws. So our goal here is trying to develop a neural network which acts as the solution operator for this hidden PDE, which automatically guarantees the conservation laws. The way of imposing physics knowledge into the neural network can be divided into two types. So the first type is basically by imposing the PDE, the kind of the governing PDE as the penalization term. So this type of approach, it has two challenges. Firstly, you have to know the governing PDE, and moreover, one need to tune an additional penalization parameter, so that could increase the difficulty of solving the corresponding optimization problem. And the second approach is what we are going to use today, is by hard-coding the partial physics knowledge into the neural network architecture. So in this work, we focus on the linear and angular momentum conservation laws. How do we impose the linear and angular momentum conservation law? We use the Noether theory. So the Noether theory, it's telling us, as far as the physical system is actually invariant on the translation and the rotation of the reference frame, then it's guaranteed it kind of has the conservation of the linear and angular momentum. So therefore, translate that into our application. That means, well, when we change the reference frame, then as far as our observation is translational invariant and the rotational equivariant, then we can guarantee these two momentum conservation laws. So here in this work, we choose the non-local neural operator as the base model. So this type of the base model has the following architecture. So firstly, the input function, so which is the G, is going to go through a lifting layer. And then we are going to get the first layer representation. So that is the H here. And then the layer representation is going to go through iterative layer. They share the same parameter. So here all the trainable parameters are highlighted by blue. So this iterative layer writes as an integral operator. So then with a trainable kernel, so that is the M here, and the local linear transformation, so that's represented by the W and the C here. Then it's going to go through an activation function, so that's the sigma here, and as the increment, and add that into the previous layer. And then after L numbers of the iterative layer, then we go through a projection layer and then get the output function. So the reason why we choose this architecture is firstly because of its integral. Basically its integral operator architecture. So when we change the resolution of our observation, then the model parameter are still reusable. So it's resolution independent. And secondly, it can be shown that this layer update, the iterative layer update, acts as a fixed point method. So which is the traditional, like the nonlinear solver for the PDE problems. So therefore, this neural operator acts as can effectively act as a universal solution operator for the hidden PDE solver. Okay, so based on this architecture, we have an additional advantage. So basically, if we try to see the trainable kernel, so that is the M as an analog as the edge feature, and then the layer update, so that is the edge here as a node feature, then this architecture can also be seen as an analog and a resemblance of a graph neural network architecture. So therefore, based on that, we can get inspiration from the recently proposed equivariant graph neural network and try to develop the invariant and the equivariant property of our architecture. So in the equivalent graph neural network architecture, the key idea is firstly, in the edge feature, we they propose to use frame invariant arguments. And secondly, they introduce an additional variable, so that represents the coordinates. And therefore, here in our architecture, we also try to adopt these two ideas correspondingly. So firstly, in our kernel, our trainable kernel, instead of using the original coordinates, we use basically the distance between two material points and also the reference angle of the bond connecting them with respect to basically the reference coordinate. And as such, it becomes frame invariant. And the second key is we also introduce an additional variable, so that is the x here, which actually evolves together with basically the layer update edge. So that encodes the rotational information and x as the coordinate in the network. So then putting everything together, we have the following resultant neural operator architecture. So then here we want to highlight that in this architecture, firstly, it still acts as the fixed point solver, and moreover, because all the interaction between the neighborhoods acts as an integral operator, so therefore the resultant architecture is still resolution independent. And moreover, we can rigorously show that this architecture is translational invariant and rotational equivariant, so therefore it guarantees the conservation of linear and angular momentum. Okay, so now let's try to see the performance of the proposed architecture on 3 exemplar applications. The first application is a benchmark problem for PDE solvers. So basically, we try to construct a mapping for the Darcy's equation from the diffusivity field. So that is the A here to the corresponding solution field. So that is the U here. And on the right-hand side, we compare our model, basically the relative L2 loss of our model with a bunch of the baseline models. So including 4 different neural operator models and the EGNN. So here in the blue, we show the results in a very small data region. So that means we only use 10 pairs of the input and output functions. We can see that in this very small data region, our invariant neural operator model outperforms all the baselines. And moreover, if we try to take a representative sample and try to translate and also rotate the reference frame, we can see that, only our model can give the invariant prediction, while our baseline model, so for example, GNO, the prediction could even blow up. Okay, so then the second example also actually comes from the material modeling. So we try to predict on the different loading scenario, what is the deformation of a heterogeneous material, the so-called glass ceramic material. And in this example, again, we try to check the performance, compare the performance of our INO model with the baseline model. So that is the GNO model in a small data region and the medium data region. So in the small data region, we can see that we again outperforms the baseline model. We reduce the error by almost 2/3, but this advantage actually going to kind of get less obvious in the median data region. So therefore, we highlight that our model is, the imposing physics loss is especially helpful in the small data region. And the third example comes from the experimental measurements. So basically, in this data, we actually try to study the deformation of a tissue leaflet. So from on the different boundary loadings. So here in this example, we highlight that it not only features basically the scarcity of data, but also it has an unavoidable measurement noise. So in this small data and the noisy data region, we again try to compare our performance. So basically the INO with 3 baseline neural operators. So that is the GNO, FNO, and MWT with respectively. So here again, in the very small data region, we can see that we can reduce the prediction error by more than 1/2.
Okay, so here is the takeaways. So we propose INO invariant neural operator model, so which acts as a solution operator for the hidden PDEs while still guaranteeing the basic physics laws, such as the conservation of linear and angular momentums. And we found that by imposing these basic physics laws, it actually improved the learning efficiency, especially in the small and noisy data region.